All right, so I am here because everyone keeps talking about coordinate geometry for these big exams, and honestly, it just sounds like some fancy football formation I have never heard of. What even is it? And why does it matter so much?
Ronaldo, that is a perfect question. Think of coordinate geometry as the ultimate GPS for shapes and points. It gives us a way to precisely locate anything in space using numbers. Imagine you are trying to describe exactly where your goal is on the football pitch. You would use coordinates, right? Like it is at 5 meters from the sideline and 10 meters from the goal line. That is essentially what we are doing, but in a more generalized mathematical way.
Exactly. Instead of vague descriptions, we use a Cartesian coordinate system. It is like mapping out a song. Each note has a specific position on the staff, a precise pitch and duration. The x-axis gives us horizontal position, and the y-axis gives us vertical position. Together, any point can be uniquely identified by its ordered pair, like parentheses x comma y's. It is super fundamental for understanding anything graphical in math.
Okay, I get the mapping part. So if I have 2 points, say my starting position and the goal, how do I figure out the direct distance between them using these numbers? In football, that is crucial for calculating my run.
Excellent question. That is where the distance formula comes in. If you have 2 points, let us call them P1 with coordinates x1, y1, and P2 with coordinates x2, y2. The distance between them is the square root of the difference in their x coordinates squared plus the difference in their y coordinates squared. It is essentially applying the Pythagorean theorem, which is about right-angled triangles, to our coordinate system.
Think of it like this. If you have 2 points on a map and you want to know the shortest straight line path between them, the distance formula gives you that. It is the hypotenuse of a right triangle where the legs are the horizontal and vertical differences between your points. This is foundational for calculating anything from trajectory in sports to distances in navigation apps.
Okay, so I can find points, I can find distances. But what if I am passing the ball to a teammate who is exactly 1/3 of the way between me and the goal? How do I find that exact spot?
That is the section formula, Ronaldo. It helps you find the coordinates of a point that divides a line segment in a given ratio. If a point P divides the line segment joining P1 at x1, y1, and P2 at x2, y2 internally in the ratio m1 to m2, then its coordinates are calculated by a specific formula. For the x coordinate, it is m1 times x2 plus m2 times x1, all divided by m1 plus m2. And similarly for the y coordinate,
it is like finding the perfect balance point on a seesaw. If you have 2 points and you want to find a point that is, say, 2/3 of the way from one to the other, you are dividing that line segment in a ratio. The section formula is your mathematical tool for that. There is also an external division where the point lies outside the segment, but internal is more commonly used for scenarios like yours.
Okay, so I can find points, I can find distances. What if I have 3 players forming a triangle and I need to calculate the area they cover? Is there a simple formula for that with coordinates?
Absolutely. There is a very neat formula for the area of a triangle given the coordinates of its vertices. If the vertices are x1, y1, x2, y2, and x3, y3, the area is 1/2 times the absolute value of x1 times y2 minus y3 plus x2 times y3 minus y1 plus x3 times y1 minus y2. It looks long, but it is quite systematic. You can also remember it using a determinant method if you are familiar with those.
This formula is super useful because it automates the process. Instead of needing to measure base and height, which can be tricky if your triangle is tilted, you just plug in the coordinates. And a cool side note, if that calculated area turns out to be 0, it means your 3 players or points are all in a straight line. They are collinear.
Yeah.
That is a quick check for linearity.
So if the area is 0, they are lined up. Got it? This makes sense for setting up plays. Now, what about lines themselves? Not just points, but how do I describe the path of a ball kicked in a straight line or the boundary of the field. There must be equations for lines.
You are spot on. Ronaldo, lines are fundamental. There are several ways to describe them with equations, each useful in different situations. The most common is the slope-intercept form, y equals mx plus c, where m is the slope, telling you how steep the line is, and c is the y-intercept. Where the line crosses the y-axis, it is like the trajectory of your kick, m being the angle, and c being where it starts vertically on the goal line.
And the slope, m, is literally the rise over run, how much the line goes up or down for every step it takes horizontally. A steeper slope means a bigger m value. A horizontal line has a slope of 0, and a vertical line has an undefined slope, like trying to climb an infinite ladder. Then there is the point slope form. Y minus y1 equals m times x minus x1, super handy when you know a point. And the slope.
So slope is the steepness, got it? What if I just know 2 points the ball passes through, say from my foot to a teammate? Can I get the equation without knowing the slope first?
Absolutely. That is the 2-point form. You can calculate the slope first using the change in y over the change in x, y2 minus y1, divided by x2 minus x1. Once you have that slope, you can use either of the 2 points with the point slope form, or you can directly use the 2-point formula, which is y minus y1 divided by y2 minus y1 equals x minus x1 divided by x2 minus x1. It is all interconnected.
And there is also the intercept form, x over a plus y over b equals 1, where a is the x-intercept and b is the y-intercept. That is useful if you know where the line crosses both axes. Imagine if your pass has to cross 2 specific lines on the field. This form would describe that. Each form has its moment to shine depending on the information you have.
Okay, so many ways to describe a line. What about angles between lines? If 2 players are making runs and their paths cross, how do I find the angle of their intersection? This is vital for tactics.
For the angle between 2 lines, if you have their slopes, let us say m1 and m2, the tangent of the angle, denoted as tan theta, is the absolute value of m1 minus m2 divided by 1 plus m1 m2. If m1 m2 equals minus 1, the lines are perpendicular, meaning they form a 90-degree angle, which is a right angle. If m1 equals m2, they are parallel. This is incredibly useful for predicting collisions or ensuring strategic positioning.
For the 90-degree angle, m1 times m2 equals -1 is your golden rule. Think of it as a perfect cross where one path is perfectly at right angles to the other. And for parallel paths, their slopes are identical, m1 equals m2. Knowing these simple conditions is a shortcut to understanding how lines relate to each other without needing to calculate the angle every single time.
Okay, that's powerful for understanding movements. What if I am trying to clear the ball and I need to know the shortest distance from the ball, currently at some specific point to a line of defenders? Is there a direct formula for that distance?
Yes, absolutely. A crucial one for your scenario. If your line is in the general form ax plus by plus c equals 0, and your point is x naught, y naught, the perpendicular distance d is the absolute value of a x naught plus b, y naught plus c, all divided by the square root of a squared plus b squared. This formula is direct and gives you the shortest distance, which is always the perpendicular distance.
This is often used in computer graphics for collision detection or in robotics for path planning to avoid obstacles. It is not just about lines, it is about spatial awareness. The absolute value ensures you always get a positive distance because distance cannot be negative. This is a formula you will want to have memorized for those high stakes exams.
Okay, so if I have multiple lines that all seem to meet at that one crucial point, like different tactical runs converging on the goal, is there a concept for that?
That is a perfect description of concurrent lines. When 3 or more lines pass through a single common point, we call them concurrent lines. Think of it as a strategic convergence. To determine if they are concurrent, you take any 2 of the line equations, solve them simultaneously to find their intersection point. Then you test if this intersection point satisfies the equation of the third line. If it does, all three lines are concurrent.
It is like three different melodies coming together at the exact same chord. For JE Advanced, they sometimes expect you to use determinants for concurrency, especially if the lines are given in the AX plus BY plus C equals 0 form. You form a 3 by 3 determinant with the coefficients A, B, and C for each line. If the determinant equals 0, the lines are concurrent. It is a more elegant, compact way to check.
Okay, that's useful for checking formation plays. Now let's talk about something round, like the circle in the center of the field. How do we describe a perfect circle using coordinates? What all its equations and secrets?
The circle, the queen of curves! Its definition is simple yet powerful. A circle is the locus of all points that are equidistant from a fixed point. That fixed point is called the center, and the constant distance is the radius. This definition is the key to deriving all its equations. It is like the perfect balance in a spin, always maintaining the same distance from its axis.
The standard equation of a circle, which is super important, is parentheses x minus h close parentheses squared plus parentheses y minus k close parentheses squared equals r squared. Here, h and k are the coordinates of the center, and r is the radius. If the center is at the origin, 0, 0, it simplifies beautifully to x squared plus y squared equals r squared. This form is derived directly from the distance formula.
X minus h squared and y minus k squared. Got it. But what if the equation looks all mixed up like a general algebraic mess? How do I find the center and radius from that?
That is the general equation of a circle, which is x squared plus y squared plus 2gx plus 2fy plus c equals 0. From this form, the center is directly found at minus g minus f, and the radius is the square root of g squared plus f squared minus c. You just need to match the coefficients. It is like transforming a complicated playback into its basic, understandable components.
The key condition for a general second degree equation, ax squared plus by squared plus 2xy plus 2gx plus 2fy plus c equals 0, to represent a circle is that the coefficients of x squared and y squared must be equal. So a equals b, and also the hy term must be 0, meaning no xy product. This simplifies it to x squared plus y squared and so on. Also, the radius must be a real positive number, so g squared plus f squared minus c must be greater than 0.
What about special cases for circles? Like if it touches the x-axis or y-axis, or if the diameter is given, are there specific equations for those?
Yes, absolutely. If a circle touches the x-axis, its radius is equal to the absolute value of its y-coordinate, so r equals absolute value of k. If it touches the y-axis, r equals absolute value of h. If it touches both axes, then r equals absolute value of h and r equals absolute value of k, meaning the center is r, or similar variations depending on the quadrant. And for the diameter form, if ax1, y1, and bx2, y2 are the endpoints of a diameter, the equation is parentheses x minus x1 close parentheses times parentheses x minus x2 close parentheses plus parentheses y minus y1 close parentheses times parentheses y minus y2 close parentheses equals 0. This is quite elegant and useful.
And there is also the parametric form, which is x equals h plus r cosine theta and y equals k plus r sine theta. This is incredibly useful when you need to describe the motion of a point moving along the circle, like a player running around the center circle. Theta is the angle from the positive x-axis to the radius line. This is particularly relevant for calculus and physics applications involving circular motion.
What about tangents to a circle? If I'm kicking the ball and it just grazes the outside edge of a circular obstacle, how do I find the equation of that path? And what if the ball is outside the circle and I want to find the lines that just touch it?
This is where tangents come in. A tangent is a line that touches the circle at exactly one point, called the point of tangency. For a circle with center h, k and radius r, and a point x1, y1 on the circle, the equation of the tangent at that point is parentheses x minus h close parentheses times parentheses text parentheses x close parentheses plus parentheses y minus k close parentheses times parentheses y1 minus k close parentheses equals r squared. If the circle is x squared plus y squared equals r squared, it simplifies to xx1 plus y1 equals r squared. The tangent is always perpendicular to the radius at the point of tangency.
For tangents from an external point, there will always be two such tangents. You can use a general tangent equation like y equals mx plus or minus r times the square root of 1 plus m squared, which is valid for a circle centered at the origin. You then substitute the external point's coordinates into this equation to find the two possible slopes m, which then give you the two tangent equations. There is also the concept of the length of the tangent from an external point px1, y1 of the circle x squared plus y squared plus 2gx plus 2fy plus c equals 0. This length is the square root of s1, where s1 is the value obtained by substituting x1, y1 into the circle's equation. It is super neat.
So a tangent is like the very edge of my foot contacting the ball for a perfect curl. What about other weirder shapes, like an oval or a path that gets narrower than wider? I've heard about parabolas, ellipses, and hyperbolas. What are those, and how do they fit into this coordinate system?
Those are the conic sections, Ronaldo, and they are incredibly important in higher level math and physics. They are called conic sections because they can literally be formed by slicing a double napped cone with a plane at different angles. A circle is formed when the plane is perpendicular to the cone's axis. Tilt the plane slightly and you get an ellipse, an elongated circle. If the plane is parallel to the cone's generator, you get a parabola. And if it cuts both parts of the double cone, you get a hyperbola. Each has unique properties and forms just like different types of strategic plays.
The unifying concept for all conic sections is their definition as a locus of points based on a focus and a directrix. For any point on a conic, the ratio of its distance from a fixed point, the focus to its distance from a fixed line, the directrix, is a constant called the eccentricity, EE. If E equals 0, it is a circle. If E is between 0 and 1, it is an ellipse. If E equals 1, it is a parabola. And if E is greater than 1, it is a hyperbola. This focus directrix definition is the most powerful way to understand them all.
Okay, so the eccentricity E is the secret key. If E is 1, it is a parabola. How do I write the equation for a parabola? And what are its special points? Like the focus you mentioned and that directrix line.
A parabola is the path of a projectile, like a ball kicked into the air, neglecting air resistance. The most common standard equation is y squared equals 4ax, where the vertex is at the origin 0, 0. The focus is at a 0, and the directrix is the line x equals minus a. The value of a determines how wide or narrow the parabola is. There are other forms too. X squared equals 4ay opens upwards. So y squared equals minus 4ax opens left, and x squared equals minus 4ay opens downwards.
Key terms for a parabola are the vertex, which is the turning point, the focus, which is a fixed point, and the directrix, which is a fixed line. The axis of the parabola is the line passing through the focus and perpendicular to the directrix. The latus rectum is a line segment passing through the focus perpendicular to the axis and with endpoints on the parabola. Its length is absolute value of 4a. These terms help you visualize and define the parabola's shape and orientation precisely.
What about tangents to a parabola? If my shot follows a parabolic path and then just touches a certain line, how do I find that line's equation? And if I know the point of contact,
for a parabola like y squared equals 4ax, the equation of the tangent at a point x1, y1 on the parabola is y1 equals 2a times parentheses x plus x1 close parentheses. If the parabola is x squared equals 4ay, the tangent is x1 equals 2a times parentheses y plus y1 close parentheses. It is a direct substitution pattern, quite similar to the circle, but you are replacing the squared terms carefully. This helps describe how your shot curves just enough to brush past a defender.
For a tangent with a given slope m for a parabola x squared equals 4ay, the equation is y equals mx minus am squared. If it is y squared equals 4ax, the equation is y equals mx plus a over m. These are general tangent conditions. You can also find tangents from an external point by using these slope forms and substituting the external point's coordinates to solve for m. This gives you the two tangents from that point, just like with circles. The normals, lines perpendicular to the tangents, are also important. Their slopes are the negative reciprocal of the tangent's slope at that point.
Okay, that's a lot of shapes. What about an ellipse? That's like a stretched circle, like an oval soccer ball if it was deflated a bit. How do I describe that with equations? What are its special points and lines?
An ellipse is defined as the locus of a point such that the sum of its distances from two fixed points called the foci is constant. That is PF1 plus PF2 equals a constant, which is 2a. Its standard equation for a center at the origin is x squared over a squared plus y squared over b squared equals 1. Here a is the semi-major axis and b is the semi-minor axis. If the major axis is along the x-axis, a is greater than b. If it is along the y-axis, b is greater than a. It is like the path of planets orbiting the sun, a beautiful, consistent dance.
The foci are at plus or minus c0, where c squared equals a squared minus b squared. The directrices are the lines x equals plus or minus a over e, where e is the eccentricity c over a. The vertices are at plus or minus a, 0 along the major axis, and 0 plus or minus b along the minor axis. The latest rectum has length 2b squared over a. All these elements define the precise shape and position of your oval soccer ball.
What about tangents for an ellipse? If I want to calculate the exact point where my shot would just brush the side of an elliptical goalpost, how do I do that? Are there similar formulas for tangents as with circles and parabolas?
They are indeed similar. For an ellipse, x squared over a squared plus y squared over b squared equals 1. The equation of the tangent at a point x1, y1 on the ellipse is x1 over a squared plus y1 over b squared equals 1. It is a direct extension of the pattern you have seen. For a tangent with a given slope m, the equation is y equals mx plus or minus the square root of a squared m squared plus b squared. Again, very structured and predictable.
And the parametric form for an ellipse centered at the origin is x equals a cosine theta and y equals b sine theta. This is very useful when you are dealing with problems that involve angles or motion around the ellipse. The angle theta is not the usual polar angle, but rather an eccentric angle. This form helps describe the smooth, continuous movement on an elliptical path.
All right, so circles and ellipses are about being enclosed. What about something that opens up forever or has two distinct parts, like if a ball breaks through a barrier? I'm talking about a hyperbola. What's its deal?
A hyperbola is the locus of a point such that the absolute difference of its distances from two fixed points, the foci, is constant. That is absolute value of PF1 minus PF2 equals a constant, which is 2a. The standard equation for a center at the origin, x squared over a squared minus y squared over b squared equals 1. This is for a horizontal hyperbola, opening left and right. The minus sign is what distinguishes it from an ellipse. The value a is the semi-transverse axis and b is the semi-conjugate axis. It describes trajectories in gravitational fields for objects escaping gravity, like a comet slingshotting past a star.
For a vertical hyperbola, opening up and down, the equation is y squared over a squared minus x squared over b squared equals 1. In this case, a is the semi-transverse axis along the y-axis. The foci are at 0 plus or minus c squared equals a squared plus b squared. The vertices are at plus or minus a, 0 for horizontal, or 0 plus or minus a for vertical. The directrices are x equals plus or minus a over e, or y equals plus or minus a over e, with eccentricity e equals c over a, where e is always greater than 1 for a hyperbola. The asymptotes, those dashed lines it approaches, are given by y equals plus or minus b over a times x for horizontal, or y equals plus or minus a over b times x for vertical. They are crucial for sketching the hyperbola.
And tangents to a hyperbola, if my shot somehow followed a hyperbola, how do I find the line that just touches it? Is the pattern for tangents still similar across all these conic sections?
The pattern for tangents is surprisingly consistent across all conic sections, which is a beautiful mathematical symmetry. For a hyperbola x squared over a squared minus y squared over b squared equals 1, the equation of the tangent at a point x1, y1 on the hyperbola is x1 over a squared minus y1 over b squared equals 1. For a tangent with a given slope m, the equation is y equals mx plus or minus the square root of a squared m squared minus b squared. Notice the minus sign under the square root compared to the ellipse. These subtle differences are crucial for distinguishing their properties.
And the parametric form for a horizontal hyperbola centered at the origin is x equals a secant theta and y equals b tangent theta. For a vertical hyperbola, it is x equals b tangent theta and y equals a secant theta. These forms are less intuitive than for circles or ellipses, but they are very powerful in advanced problems, especially those involving calculus or physical phenomena that naturally follow these paths.
So we've got circles, parabolas, ellipses, hyperbolas. Is there one master equation that covers all of them? Or are they all completely separate creatures?
That is an insightful question, Ronaldo. There is indeed a general equation for all conic sections. It is a second-degree equation in x and y, ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. The type of conic it represents depends on the discriminant, which is b squared minus 4ac. If it is less than 0, it is an ellipse or a circle, possibly a point or no locus. If it is equal to 0, it is a parabola or parallel lines, coincident lines, or no locus. If it is greater than 0, it is a hyperbola or intersecting lines. This general form is essential for a comprehensive understanding.
And for JE Advanced, you will sometimes encounter problems where the axes of the conic are rotated. That BXY term indicates rotation. If B is 0, the axes are parallel to the coordinate axis, which makes things simpler. But if B is not 0, you would need to perform a rotation of axes to transform the equation into a standard form without the BXY term. That is a higher level transformation that ensures you can always simplify any conic back to its fundamental orientation.
Wow, so even if the shape is tilted, we can still figure it out? That's powerful. One last thing, can we summarize the normals? We talked about tangents, but what about the lines that are perpendicular to the tangents at the point of contact? Is there a general method for all conics?
Yes, the normal is simply the line perpendicular to the tangent at the point of tangency. Its slope is the negative reciprocal of the tangent's slope at that specific point. So once you have the tangent equation for any conic at a point x1, y1, you can find its slope m tangent, then the slope of the normal will be minus 1 over m tangent, provided m tangent is not 0. You then use the point slope form with x1, y1, and the normal slope to get the normal's equation. This applies to all conics, and it is a key concept for understanding reflection properties and other physics applications.
This general approach for normals is incredibly powerful because it is universal across all these curves. It is the mathematical way of finding the direction perfectly perpendicular to the curve at any given point. This is used in everything from designing optical lenses, where light rays reflect along normals, to understanding how forces act on curved surfaces. It is a fundamental concept for JEE Advanced, binding all these individual shapes together.
Okay, that's a whole new level of understanding for me. From plotting my runs to predicting where the ball goes, and even understanding how light works on curved surfaces. This coordinate geometry is like the ultimate playbook for shapes and movements. I feel like I could strategize an entire match just with these equations. Thank you all for breaking it down. It's way more interesting than just numbers on a page.
You got it, Ronaldo. Coordinate geometry is truly the bedrock for so many fields. From architecture and engineering to physics and even computer graphics in video games, understanding these equations allows us to model and predict the world around us with incredible precision. You can see now how everything, from a simple point to the most complex conic sections and their interactions, fits into this elegant mathematical framework.
And for anyone preparing for exams like JE Advanced, mastering these concepts is non-negotiable. It is not just about memorizing formulas. It is about understanding the logic behind them, how they are derived, and how to apply them flexibly to various problem-solving scenarios. That is when you truly unlock the power of coordinate geometry. It is the language of shapes, and now you are fluent. You have nailed this deep dive.